If you walked into my room right now, you'd find a lettuce plant growing inside a sealed acrylic pod with sensors, fans, and a small air pump. And no, I'm not trying to grow salad for space, although that might not be far off. Hi, my name's Ian Wright, and this is my project called EcoSphere. This is a self-regulating hydroponic growth chamber designed to test how tiny changes in air pressure and carbon dioxide concentration affect plant growth efficiency. The main goal of my study is to manipulate and optimize the microclimate inside a hydroponic system to increase the plant growth efficiency, essentially getting more lettuce per drop of water. The hypothesis is that by increasing CO2 levels to about 6,000 parts per million and slightly lowering total air pressure to around 90 to 95 kilopascals, I can improve gas diffusion in the leaf, boosting photosynthesis while minimizing water loss. My project specifically targets the science behind plant growth through photosynthesis and the gas diffusion equation. See, plants exchange gases through microscopic pores in their leaves called stomata. These pores open and close throughout the day, allowing carbon dioxide to diffuse in for photosynthesis while letting water vapor escape in the process of transpiration. This creates a constant trade-off. To gain carbon, plants inevitably lose water. The efficiency of that trade-off, how much carbon is fixed per unit of water lost, is known as the water use efficiency. A high water use efficiency means that a plant is photosynthesizing more effectively without excessive water loss. Zooming in, we can see that carbon dioxide diffuses from the air through the stomatial opening, across a boundary layer, and finally into the intercellular spaces where photosynthesis occurs. This diffusion process follows Fick's law, which states that the rate of gas movement depends on the concentration gradient and the diffusivity of the gas. However, because total pressure affects all gases, the system needs balance. Too much pressure reduction would also lower the partial pressure of CO2. Thus, the driving force for diffusion would decrease. That's why this experiment combines moderate CO2 enrichment with a small pressure decrease. The goal is to enhance diffusion without starving the leaf of the material it needs to grow. Together, these changes are expected to increase carbon assimilation relative to water loss. To test my hypothesis, I'm running two growth conditions using identical hydroponic setups. In the ambient condition, the system is open to the room, exposed to regular pressure and ambient CO2 conditions. In the controlled condition, the ecosphere is sealed. The CO2 is enriched using a sugar yeast reaction and maintained at a slightly lower pressure using a diaphragm pump. All other variables are kept the same. Various sensors record data such as temperature, humidity, pressure, and CO2 levels every 10 seconds, while the water and plant mass are measured daily. The metric of measurement is the overall growth efficiency. I'm measuring the grams of plant biomass gained per liter of water used. All of my sensor data is being logged on an onboard SD card and averaged over 5-minute intervals. That data will show me how well the system maintains its target environment. Things such as staying within the pressure band of 90 to 95 kilopascals and holding a CO2 level near 600 parts per million. I'm going to compare the water use, growth rate, and microclimate stability between these two conditions. Based on well-established plant physiology models, I expect to see around a 10 to 15% improvement in growth efficiency with my controlled setup. My hope is that systems like this can eventually inform controlled environment agriculture in extreme places, whether that's northern Canada or who knows, maybe Mars one day. Thank you for taking the time to learn about optimized plant growth and the research I'm currently conducting to push this field forward. Until next time.